let's start. Actually, Hari is going to join us, I guess, as soon as. What? He hasn't yet replied, but because everybody else is there, we'll start, and then when Hari comes, we'll just patch him in. Okay, so welcome everybody to Yuheng Hu's PhD Defense. Besides me, the committee members are Wan Lu, who apparently these days comes to visit ASU mostly to attend my students' defenses. He's away. Dr. John Crum for Microsoft Research, who I understand woke up at 3 a.m. this morning in Redmond and packed the Seattle weather and came here to be in person here. And Eric Horwitz, who is on the Skype, also of Microsoft Research, who is going to be participating via Skype. And Professor Hari Sundaram, who went away to some place so that he would actually experience firsthand how hard it is to do remote defenses. But he's not here right now. Hopefully will join soon. And then I'm also very happy that Ajita John is participating because Yuheng actually started some of his early work with an internship at Avaya with Ajita. So that's the committee, and I want to say a few words before Yuheng starts off and does his formal defense. Yuheng received his bachelor's at Zhejiang University. I believe that's the correct pronunciation for those of you who don't know how to say it right. And master's at Florida International University before joining as for PhD in 2010. And his PhD work that he's going to be describing today is on sort of automated analysis of social media, and it's had some interesting impact. He has citations, and he also received some best paper nominations and also lots of media coverage. Pending successful defense today, he plans to join IBM Almaden as a research staff member. So a couple of personal words about him. So there are PhD students who allow themselves to be steered by their advisor. There are PhD students who are somewhat harder to steer, and then there are those who turn around and steer the advisor instead of being steered. I've had my share of this third category of students, but I think Yuheng is the leader of that pack. He has sort of convinced me multiple times that these are the interesting things we should do, and apparently I somehow agreed to, and I think he's actually right. That he's done very neat work. He's forged a lot of fruitful external collaborations during his time at ASU. Obviously, Ajita, Eric, and John have worked with him, as did Shelley Farnham at Microsoft. He also co-opts very well the students in my lab to work with him on things that he's working on. So Lydia and Karthik have shared very interesting papers with him. So Yuheng is probably one of the students with a very good sense of impact of the work. He chooses problems that he knows will be sort of first in some category. There's this 21 rules of marketing. The first rule of marketing is be the first in your category. It's better to be first than to be better. And the second rule is if you can't be the first in the category, make a new category. He knows how to do that. So he has basically never. I think he tries to write papers that he knows will have some amount of impact, and I think that's been to some extent validated by the sort of citations he gets, as well as various people trying to write up on his work in the media. He's also an amazingly hardworking student. The times when he's actually at ASU and not in Seattle, visiting supposedly his girlfriend, he's all the time in front of the machine, working all the time, and then when he goes off on holidays, supposedly to be with his girlfriend, he writes a couple more extra papers overnight. So I think his understanding of taking rest seems to be somewhat flawed. There are several reasons I think I'll miss him when he graduates, but I'll just to mention two. First thing, he makes me looks good. He actually made me look good when I was on TV trying to explain his work. The second is there are these Yuheng chat bulletins. My other students send me an email and wait for me to respond at a time when I want to. Yuheng sends a chat. In the middle of the thing, it'll be ping, and then you have to go run and see what Yuheng wants us to do. And these chats involved all sorts of interesting things in addition to technical things, great gossip, academic gossip, and many a time I learned what was happening even in this department because he told me so, not because I knew what was going on. So I guess I will live in dark Because I think Yuheng seems to have a premium access to the ubiquitous sensor network of expat Chinese researchers who seem to know exactly what's going on anywhere, and he knows and tells me. I think I'll miss that, but then I guess I'll have a easier sleep because my chat thing won't be going off ping all the time. Anyways, that's all I have, and I think Yuheng did very nice work, and he tried to defend it. Let's hear it.
Thank you, Al. Thanks for very kind words. So before I started, I just want to say, so like father, like son. So Ralph, you're truly my, academic father. So I just want to. I also prepared a small thing I want to say just before my defense. So first, I want to thank my advisor Ralph, and you're the most wonderful advisor a grad student can ever hope to have, and you give me enough freedom, intellectually and physically, to pursue the interests that I want, and enough guidance to keep my work relevant. So Rao, I cannot thank you enough. And second, I want to thank Eric and John. And working with you have broadened my perspectives, and I enjoyed our conversations a lot. And thank you for everything. And what I want to point out is that what Ralph said about Seattle is halfway true. Actually, my girlfriend actually complained about that. She always tell me that no, you are not here to see me. You are here to see Eric and John. And
tell her I felt the same way.
Okay. Well, and I also want to thank Professor Harvey Sunram, who is not here, unfortunately, yet. And he basically brought many angles to my research, which I never think of, and I very appreciate that he set a very high bar for me to be a true scholar. So I want to thank him as well. And I also want to thank Professor Huang Liu. Thank you for encouragement, and most importantly, I want to thank you for having such a group of understanding students who gave me tremendous amount of peer pressures in the past few years. And I often get fixed feelings after learning that, okay, your group have another 5 papers accepted. And I'm happy because, they are my friends. But I'm also worried so much because, I have to keep working hard. And thank you very much for doing that, and it keeps me always highly motivated. And also I want to thank Ajita. So you are my first mentor who, brought me into the area of social computing, and without you, I don't know, I cannot stand here to defend this work. And last, I want to thank everyone here for your time, especially the ones who came here from Seattle. All right, so let's get started. So today I'm going to present my dissertation work on semantics analysis on social media. So basically, I'll talk about the challenges in leveraging vast amounts of social media data to analyze events, and I will also present our technical solutions, as well as some of the insights that we learned. So events, right? So people have a long history of dealing with events, just like this painting tells us. Like over 3,000 years ago, people from Greece they have already found a way to discuss about events. For example, they will gather in a town square like this in Sunday afternoon and exchange their ideas about what's going on in the event, who is the most important person in the event, and things like that. But due to the technologies at the time, that most of their chatters they cannot be saved. So there's no way, it's very hard for us to understand what those people actually talk about during that time. But thanks to social media, that it has created a sprawling virtual town square, which scope is vast, and the most importantly, the chatter on social media can be saved. So given the vast amount of social media data generated during the event, it opens a tremendous opportunities for us to analyze, okay, what's going on in the event, what the sentiment looks like in the event, what's the influence of the event on people's behaviors, right? So the main focus of this dissertation, of my research, is that I want to develop, automated solutions to conduct in-depth analysis of using the social media data to understand, understand those kind of events. So let's look at what kind of events that that can be talked about on social media. So I want to use this particular example here as a motivating scenario, but of course my techniques can handle events beyond this kind of particular events. So. So 2014 Hong Kong protest is an ongoing event. It started in September of this year, and it's still on it. And why people have this protesting is because that they want more, the transparency and democracy in electing their own leaders. So over the course of 2 months, around like 1 million people, Hong Kong citizens, they just gathered together and they occupied major city intersections or sit in front of the government buildings to do the protesting. But this event becomes very controversial after those people, as you can see here, they just live on the street, they occupy the street, and which create a lot of trouble for the public, transportations because they occupy those, city intersections. So a lot of people, the working class, they have to do a lot of detour at the time because the public transportation somehow is shut down. And to avoid this situation, basically, police use the tear gas to disperse those people, which also create a lot of criticism because a lot of people say whether this is overreacted or not. So as you can imagine that given this kind of dynamic, controversial events, there's a tremendous of social media, responses that on Twitter, on Facebook, we talk about this, right? So given the events like this and given the social media data like this, so what kind of question that we want to answer? So the first question, the first research question in my work is that given events and given tweets, what were the topics of the event and tweets, right? We want to extract the topics from the events, we want to extract the topics from the tweets. So after that, we want to learn, okay, what were the sentiments of the event's topics? Whether people support this, Occupy Hong Kong or sitting in front of the government building, or they disprove that, right? We want to see the sentiments. And next, we want to recognize those kind of trending events from Twitter stream. Why this is important? Because some of the events that we do not know in advance, some like breaking events suddenly happen in one region in Hong Kong. So a lot of people may start tweeting about this. So how do we automatically detect those kind of tweeting events and feed it back to the maybe other people like journalists? Because those kind of newsworthy breaking events might be of very high interest to those people. And the last is that how do we get additional event information? So let's assume this journalist right now is covering the events happening in this region. And suddenly there's a breaking event happening here. And it is nearly impossible for this guy, for this journalist to travel from his current location to this event's location because he's occupied here to be covering what's going on in this region. So how do we leverage the wisdom of crowd to help him to get enough first-hand information about this event from the field? So how do we address these challenges? And why do we want to address these challenges? This is because that event analysis has a wide range of applications. For example, the computational journalism, political campaigns, civic engagement, event playback, storytelling, and things like that. But you can imagine that people in industry like the news agencies, they already recognize the value of social media in reporting, those kind of events. So this is a screenshot of how people, which we call event masters, dealing with vast amount of social media data to report the midterm elections in the past few months. So what they do here is that they just sit in front of the computers and they monitor social media response like tweets one by one to check which one is interesting, which one is newsworthy, right? After that, on many news websites like CNN, you will say, okay, this manual pick interesting tweets, they will put, next to their stories to argument people's experience dealing with those events. But however, we want to argue that, given the vast amount of social media data here, those manual inspection is time consuming, is very, very costly, and it's nearly impossible because, how come a person can handle millions of tweets, one by one? Therefore, we do need automated solutions to handle, to understand those Twitter events, to dig out the insights. So people in computer science, computer scientists like to develop all sorts of automated tools. But unfortunately, the most existing tool that, so far on event analytics are either primitive or ignore the complex connections between the events and its Twitter responses, for example. So by primitive here, I mean that most so-called state-of-art work is about the word cloud, right? So they basically visualize the word, the word in bigger font if it is important in this event. And for primitive, for the second part, basically they treat the events which is independent of the responses. So we start the events alone, and then we start study the tweets alone, and then they will do some kind of analysis. But I will show you later that this joint analysis can enable much more rich perspective that's never studied before and can provide a much more accurate analysis. So what are the goals here for my work, for the data teaching, which is, given the vast amount of social media responses and the complex nature of the events, we not only need the automated solutions to understand those data, also we want to do in-depth analysis. So what kind of analysis we will do, and I will show you later. But before that, I want to talk about the technical contributions here of my research. So the technical contribution here is that I proposed Event Radar, which is a comprehensive event analytics toolbox to handle 3 core event analysis tasks. So given the tweets volume, the incoming tweets volume, so the first task we want to do is what we call event characterizations. So we want to characterize the event in terms of its topics, segments, the influence of the events on the people, and how people's tweeting behavior were affected by the events, and as well as the sentiments. And the second task we want to do is what we call event recognition. Basically, we want to detect the trending events from a stream of noisy tweets. And the last task we want to do is which we call event enrichment. So basically, we want to get additional event information, the additional first-hand information.
Oh, Hari is calling. Okay. If you do, what happens?
Also with video?
Yeah.
Yeah.
Hold on a second.
Okay, there he is. Hi, Hari.
Hey, sorry, for some reason on my calendar it's 3 p.m. I'm so sorry.
Okay.
Here. Okay.
So can you put them?
Okay.
Just make sure that the entire set is back again.
No, I think it's because of the daylight savings. Sorry.
Okay.
Oh, okay. So let me help you, and then I will put you in a group chat. So.
Here, I'll let you do it.
Okay.
Oh, good. Well, I think he's. Yeah.
Where is Hari?
Hari is the separate. No, it's here. Oh, this is like. Well, Skype is Microsoft technology, so I'm pretty sure it will work. Eric is here, John is here, to make sure
it has
things
to
will
work.
Hari, I cannot see your video.
Okay.
Ask him to have.
Alright.
But yeah, that's fine. Yeah. Okay, go ahead.
Still loading.
Okay. Perfect.
Great. Thanks.
All right. Okay. So, yes. So basically, what I do in the technical contributions of this dissertation is that I propose this event radar toolbox. It's an automated toolbox to handle 3 core event analytics tasks. The event characterizations, to learn event topics, the sentiments, the responding behaviors, and the influence of the event on people's behavior, the influence of the events. And the second task is event recognition. Basically, we want to detect the events with its associated tweet volume, tweets from a volume of very noisy tweets. And the last task is we call event enrichment. Basically, we want to gather the additional event information, the first-hand information about certain events to enrich the event context. Okay, so let's look at what kind of, specifically what kind of tool that I developed here. So the first tool which I developed is called ETLDA, which is a very powerful automated tool to do a lot of things at the same time. So what ETLDA does is that given events like Obama-Romney debate, and given some kind of textual document to record this event, which is such as a transcript, such as a news article, about this event, or like a play-by-play, description about this event. What ETLDA is capable of is that it can first automatically segment this event, the document about this event into a set of segments, where each segment talks about a particular set of topics. And in the same time, ETLDA will automatically classify tweets into 2 types, the specific tweets and the general tweets. And for the specific tweets, ETLDA can also automatically establish the alignment between a particular segment and these specific tweets. And what do we mean by specific tweets and general tweets? Let me give you an example. So specific tweets means that the topic of these tweets is specifically about the topics of the event. For example, a specific tweet can be what Obama said about healthcare was wrong. So that's very specific, just about Obama's topic, Obama's comments or his speech on healthcare. Versus the general tweet is like, I don't like this debate at all. So this very high level can post at any time of the event, right? So after establish the alignment by the ETLD model or learning the topics, the segments and the inference of the event, what else we want to do here is that for this event characterization task, we want to learn the segments. So we want to learn, okay, for healthcare, the topic of healthcare, whether people like it or not, based on their opinions expressed on Twitter. And for immigrations, whether people like it or not. So we want to learn, okay, what sentiments looks like. And also for the second task, which is the event recognition task, what we want to do here is that we want to detect the tweets from detect the events from Twitter streams. This is a paper in Kai, which won the best paper nominations. So we developed an unsupervised event detection algorithm, which we call DEMA. So what DEMA can do is that given a raw noisy tweet like this, DEMA will look at each individual terms and monitor whether it is uptrending at a given time period or not. So if it is uptrending, trending terms or features we call, DEMA will automatically group them together to form event clusters, where each cluster means represent one event. And on top of that, DEMA will also automatically summarize those tweets, those tweets in the event cluster, and by picking certain keywords. So as a result, given the tweets like this, so DEMA will automatically detect, okay, so there's a fire happened at 5th Street and Pike, and those heard sirens and lots of smoke, those kind of keywords, uptrending keywords, are automatically summarized by DEMA. So based on DEMA, I developed an interesting system called Huli. So Huli basically is a web interface to facilitate the information seeking for the local communities, right? So using Huli, you do not need to look at Twitter, right? By just using Huli, you can easily learn, okay, what's going on in my local neighborhood? Who are the most popular neighbors? What are the most popular topics in my local neighborhood? And also, what are the most popular places that the people check in? So by just using Huli, you can learn a lot about your local neighborhood. So next, for the last, the task, which is the event enrichment task. So basically, what we do is that we develop a CrowdX systems, which is the first general spatial crowdsourcing framework to date. And what CrowdX can do is that, let's assume there's events happening in this region, right? And there's a journalist right now is occupied, is doing some kind of investigation here. But in the same time that there are other breaking events happening in this region, and it is impossible for this guy to move from here to this events because he's occupied, right? He's doing his investigation here. And even if he can move to here, it is very likely that this event at these different places will be over. So once the event is over, it's not that newsworthy compared to when the event is happening right now. So he had to rely on some systems to help him gather information. Say I want the videos, I want the photos about this event. So what he can do, you can use the DEMA system. You can use the CrowdX systems. So basically, CrowdX can automatically identify capable workers around those different event spots and send them requests. Say take 5 photos at this region, and after that I will pay you $5. Right? So once the user here or the worker here accept the request and complete the task, so they will send back their collected photos or videos, to the journalist. So therefore, as a result, the journalist does not need to come to these different event spots or events in person, but can still able to get enough first-hand, very fresh information about this event. So next, so the previous 3 or 4 tools, the ETLD, the SOCSAND, the DEMA, and the CrowdX, basically is included in my event radar toolbox. And essentially, what we talk about for the event radar toolbox is that we leverage the input social media stream and to analyze the events. But however, little is known about the input stream itself. Therefore, we did another 2 very interesting analyses to understand first what kind of factors affect people's engagement with the event. So based on our regression analysis, we can learn a lot of interesting insights, such as people's engagement event is somehow affected by this guy's previous Twitter activities like that. So, and also enabled by this computational power in my toolbox, in the event radar toolbox, we are able to look deeply about what kind of patterns of people's engagement on Twitter, like what kind of behavior, what kind of retweeting or responding behaviors, such as specific versus general, how people tweet specifically versus how people tweet generally, with respect to the timeline or the embodying of the events. So here's a quick summarization of my contributions in the dissertation. So I have both the technical contributions as well as the scientific contributions. For the technical contributions, we propose this event radar, a toolbox to handle 3 core event analysis, tasks. The event characterizations, we developed ETLDA and SOX, and for the event recognition, we developed DMI and also its applications pooling. And for the event enrichment task, we developed the Crowd X system. And for the scientific contributions, we gain deep insights into what kind of factors affect people's engagement with real-world events on Twitter, and what kind of pattern that we can learn. So my work has been, received some honors, and in past few years. And this is a letter from Mike Rowe, who is the president of ASU. He wrote me a short letter, a very nice letter, give me some good words about my research. And I also won a Best Paper nomination award at CHI last year. So my work also received some major media coverage, both internally and externally, such as we covered our work on event analytics, covered both ASU Inner Circle and the ASU News. And externally, our work has been covered by the ABC News, the PBS, the Seattle Times, and so on. And my work also gave Ra an opportunity to show off his fancy suit. So this is him in suit, in case you wonder what Ra looks like in suit. So this is Ra, had a kind of interview in Arizona Horizon TV program like last October, I think, and to present our work on analyzing events using tweets. All right. So this is the outline of today's talk. So I will go through the technical contributions, and next I will talk about some kind of scientific contributions. So first, let's talk about the first tool in this event radar toolbox, which is the ETLDA. So for the event characterization task. So here, the event characterization task is that we want to learn the topics, the segments, and the inferences, right? So given events like the debate, for example, debate, and some kind of text or document about this debate, like play-by-play document or summarization document. And what we want to do is that we want to learn, okay, what were the topics of the event and tweets, and what's the relationship between the event and tweets, and what part of the event is a tweet refers to, right? And what kind of, how do we quantify the event inferences on tweets? So, given the goal like this, so there are several, requirements that we want to do. So the first requirement here is that we want to extract topics in events and tweets. And also we want to do is we want to segment the event into topically coherent chunks, right? We want to segment the events into different segments. And also we want to establish the alignment between the events and tweets. So we want to say, okay, how the event is reported or being tweeted by people and on Twitter. And last, we want to measure the influence of the event on its associated tweets. So here are several challenges to realizing those kind of vision or those kind of a goal. The very challenging task, the challenging problem here is that both the topics and the segment are latent. So topics are latent, and the segment boundary are also latent. How do we discover those kind of latent information? And second, when people responding to the event, they have very distinctive kind of tweeting behavior. So they can tweet very generally, about the high level and about the event, or they can tweet very specifically, very concretely related to specific segment of the event, right? So how do we model those kind of two distinctive tweeting behaviors here? And the last is that so the event is formed by sequentially ordered segments. and each of which talks about a particular set of topics. Again, the topics here are latent, right? So how do we, do the event, segmentation is because the topic are latent. So we need a way to do this. So, people may think, okay, the event was generated, and on this side on the right side we have the generated process for tweets. How tweets were generated? So they're connected because we model the interdependency between these two based on the topic inference. So we have this link here to basically transfer the topic inference on the event to the tweets. And also we have a bunch of variables to compute the different distributions here. So the technical details here are in my dissertations, and you can refer to I think the second chapters of my dissertations about the technical details of this model. But I want to highlight here is that learning this model, right, is actually very hard. It's a very hard problem. Why is that? So let's assume that we basically want to learn this joint distribution, but due to the the coupling between the hyperparameters or latent variables like here, the inference, the learning is intractable, right? So therefore, we need some kind of approximation inference scheme or inference algorithms to help us learn those kind of distributions. The one scheme we used here is called deep sampling. So basically, deep sampling, what deep sampling does is that it approximates the posterior distribution by iteratively updating the variables, some latent variables, by fixing the remaining variables. So we can derive some kind of deep sampling, update rules like this, and we can, run a couple of, iterations until the model gets stable, and learn the posterior distribution is sort of a very good approximation of these two maybe, distributions here. So here the evaluation of the ETLD model, and we compare it with some state-of-art, baselines. Of course, the more details are in the dissertations, but I want to highlight some here. So since ETLD model does both segmentations, tweets classifications, and alignment. So for the performance of the segmentation here, we compare ETLD with LCSEG, which, as I said earlier, is a state-of-the-art HM-based segmentation tool. And we can find the ETLD can achieve much better performance than LCSEG in terms of the lower error rate. And also, this is the alignment result compared to ETLD and LD. And again, the ETLD performance is much better. And it's also statistically significant. To summarize here, the first tool in this event beta toolbox is that, so the ETLD basically is a joint Bayesian model to learn the topic, the latent topics, the segments, the inference of the event on tweets. And it concurrently segment the event and classify two types of tweets, either general tweets or specific tweets. And also we demonstrate that the ETLD basically model can achieve much better performance. So next, I want to go to the second tool for the first task. So we want to learn here, what kind of sentiments, right? We want to characterize the event in terms of its sentiment is expressed in people's tweets. So, okay, here's the general problem. So given the events, and given tweets, we want to know whether people like, or either positive or either positive or negative. And as you can imagine, those kind of sentiment analysis about the event have a wide range of applications, like stock markets, right? People find a way that find the correlations between the sentiments and the stock markets. And so here the problem definition. So given a event transcript or some kind of textual documents about the play-by-play documents about the event, and it's associated with T, we want to find the aggregated sentiments, either positive or negative. Here we only consider two types of sentiments, but our model can easily handle multiple, more different degrees of sentiment here. And we want to basically find, okay, the aggregated sentiment, positive or negative, about the segment and about the topics of the event that people expressed on Twitter. So sentiment analysis, as people know, that has been a research topic for many, many years. And there's a lot of tools that have been developed to do this job. So, okay, so one may say, oh, why not? Let's say, let's get, some training data, right? Let's manually label the tweets based on their sentiments. And then we can apply it off the shelf. We can train those classifiers, such as the min card here, to train the classifier. And then we can apply to tweets to learn their sentiments. And then we can relate the aggregated Twitter sentiment to the segments and to the topics that occur within the time window around the tweet's timestamps. But do you think that this possible scheme or possible solution works? Unfortunately, it's not, right? It's not sufficient. Why is that? Because the first problem or first drawbacks of this possible solution is that it's very difficult to relate a Twitter sentiment to segments and the topics of the event. So basically, we want to see that the fixed window approach does not work, and as presented in the ETLDA work, which I will highlight later. Basically, what we discovered here in reality is that people can actually talk about the topics of the event regardless of the current development of the event. So people can talk about the topics of the event that even before it comes, which I will show you some of the very interesting insights later. And the second drawbacks or the challenge here is that, I will know, right? To manually annotating the sentiments of a vast amount of tweets is error prone. So to get a very high quality training data is always very costly, time consuming, which presents some kind of bottleneck to learn a high quality model, high quality sentiment classifier. So the last drawbacks, a challenge here is that the Twitter sentiment basically conveyed by very highly domain-specific context clues. As we know that people can say random things on Twitter, they can even create vocabularies, even very interesting words to describe the same thing. So given the dynamics of tweets like this, so if a model is static, then it can not handle these kind of situations. So how do we overcome those challenges? So we proposed a very interesting matrix factorization model, which is called SOCSENT. Basically, SOCSENT leverages 3 different prior knowledge to handle this challenge, which I presented just earlier. So the first prior knowledge is that we use the result of the ETLDA to align the tweets and to the event to handle the first challenge. And next, since the SOCSENT essentially is a semi-supervised framework, it only requires a small number of label data, so which avoid a person to learn or to label a lot of training data. So it just requires a small number of training data. And the last one is that we use a sentiment lexicon to avoid the third challenge. So by sentiment lexicon, one can easily add or update this sentiment lexicon with newer words, as long as you know its sentiments. So SOCSENT basically incorporates those 3 different prior knowledge into a matrix form, right? So it does the matrix factorization, which learns the factors in 3 latent dimensions: the segments, the topics, and the sentiments of the event, as expressed on Twitter. So here's a kind of sort of visualization of how SOCSENT works. So given an input matrix, a tweet term matrix, right? So each term is like a vocabulary. Given an input matrix like this, we want to factorize into 4 small matrices: tweet segment, sentiment, topic, segment, topic, sentiment, and turn sentiment transpose. And because we said, okay, we have 3 different prior knowledge, right? So we want the factorization to respect the prior knowledge as much as possible. So we have different 3 prior knowledge, 3 matrix form prior knowledge to constrain the learning, to constrain the learned small matrices here. So why this is important? Let me give you an example. So let's say I have a very big integer number, right? And I ask you, okay, let's factorize into 4 small factors. So without any constraints, we can factorize into different multiple, random ways. Now I say, okay, so the first factor is between 1 to 10, and the second factor is between 15 to 20. So you cannot, given the constraints like this, you cannot randomly factorize, the big integer numbers, right? So this, prior knowledge, 3 prior knowledge here, does the same thing. So we model this factorization process as a optimization problems. So essentially, we want to basically minimize the factorization errors, and at the same time, we want to factorize the small matrices to respect the prior knowledge as much as possible. So as a result of these factorizations, we can readily learn what we want to know, right? So by T times S, the 2 matrix, the product of these 2 matrices, we can learn, okay, what's the sentiment, what sentiment about event segment. And by G times T times s, we can learn, okay, what kind of sentiments of tweets and so on. And learning this model again somehow it's also very difficult because the coupling between those GT, SF, the different four matrices. So therefore we have to develop some kind of approximate algorithms. The one scheme we use here is called alternating optimization scheme. Basically, by using those kind of updated rules, you can iteratively update the different factors until the model can converge. So here is a quick overview of the performance. The performance of Soxan is actually very good. And we basically compare the performance of Soxan in classifying the event sentiment, the segment sentiment, compare that with the state of the art. And we found in general, Soxan improved the state of art by 7 to 18%.
I have a quick question.
Yeah.
So where did you get the ground truth?
Oh, ground truth we have the student to label in exchange for the course credit. We have the student from Rao's class.
Grades are easy to get.
Yeah. Okay. So to summarize, so Soxan is a kind of low-rank representation of the event tweet sentiment, and with 3 different prior knowledge to regulate the factorization process. And we also demonstrated that Soxan significantly, outperforms the traditional state-of-art tools. Okay, so next I want to talk about the second, event analysis task, which we call it event recognitions. And so here's the problem. So we want to detect the trending events and their associated tweets from a tweet string. A very noisy tweet string. So why we want to do the trending event here, right? Other than the other type of events. So first, so there in general, there are 2 types of events, either planned events or unplanned events. For planned events, we know, okay, this event will happen at this time at this location. For unplanned events, we do not know when it will happen. So there's no way for us to kind of, to detect those kind of events, right? We have to leverage some kind of signal that we can recognize the event. So one particular signal we use here is whether it's trending or not. So which we can we can quantify. So event recognition on social media has been a very hot research topic in recent years. And the state of art is that there's many different approaches, but they have some drawbacks. First, they are unable to locate the time period of when the burst happens. So they do not know when the trend starts, essentially. And second, for this existing the state of the art solution is that they are unable to differentiate whether the detected event is novel or not. They cannot distinguish whether this is a repeated event or not. And last, the most existing solutions are either domain specific, and because most of them are supervised, so you have to train on very specific domains, and such as the sports events. So you have to get a lot of very the performance of this approach are good. I mean, as long as you can get very high quality training. And so to avoid those kind of drawbacks, we proposed a DEMA. DEMA, which is an unsupervised event detection algorithm. How it works is that given a stream of your messages like tweets, and it first identify the trending features, and then it ranks the trending features based on their novelty score, which will be defined later. And next, it will group the trending feature into the event clusters, where each cluster represents one events. So how do we identify the trending features? So by trending here, we mean is that trending. This is a particular definition of trending. Is that a time interval of which the rate of change, the rate of change of momentum is positive. So people in stock markets, in finance, they work their lifetime to capture those trends, right? So we use some of the time series analysis tools from finance, such as the EMA, which is the different moving average, to capture the trend, to say whether given a time period, whether the words or the features are trending or not. So once we detect the trending features, the next step is that we want to rank them. Why that is important? Because based on my experiment, yes, we can definitely detect given a time period a lot of trending kind of words, such as good morning, right? So every day from 8 a.m. to 10 a.m., my algorithm will tell me, okay, good morning is off trending. This is, of course, that's because a lot of people will tweet about saying, good morning, it's a good day, something like that, between 8 a.m. to 11 a.m. but this is not interesting actually because it's repeated every day. So therefore, we need a way to rank by their novelty, like how rare this event happened. So we do it that we develop this kind of very straightforward ranking scheme by comparing the time series data for the feature and compare it with the mean value. So by feature, basically we mean that okay, this is here in DIMA algorithm, one feature means one word in tweet. And the next, after we have these trending novel features, what we do is that we want to group them together. We want to group the tweets. We want to group these words together. Based on their topical, the topics. So what we do here is that we use some kind of standard sheriff's neighbor, sheriff's key nearest neighbor algorithms to do the clustering. And as a result, each cluster will form a sort of event cluster, and each cluster will represent what are the trending novel feature or trending novel words about this event. And we did some evaluations on DIMA and compare that with the state of art, and we find in general DIMA is pretty good and achieves lower error rate. And to summarize, the DIMA is the unsupervised event detection algorithms to handle the event recognition task, to detect the event, a trending event from a stream of noisy tweets. And it is able to find the trending features and their associated tweets and automatically. And the performance it's quite good. It's all performed the state of art algorithms. So based on DIMA, we then developed Huli, a very interesting application of DIMA. So let me give you some motivations of Huli. So assume that a very peaceful Sunday afternoon, right? So you're at home, you're probably watching TV or like that, and suddenly you're hearing the sirens blaring in your neighborhood. It's very loud, and you go to the patio to say what's going on, right? And you can also check the local TV news, right, to say what's really going on in the local neighborhoods. Or you can check the local newspapers online to say whether journalists are aware of those kind of events. But in most cases, unfortunately, the search will be fruitless. Why is that? Because in general, journalists or news agencies are quite slow in reporting those kind of very fresh events. But if you turn to social media, perhaps your neighbors are reporting those kind of information on Twitter, such as these tweets, right? So basically, this guy says, there's no significant damage, it's just a small kitchen fire. So your neighbors probably reported this, what kind of sirens, there's small fires, there's, ambulance, there's people are reporting this. But the thing is that, although social media is fast-paced, right, it's ubiquitous, a lot of people can report this, but social media is also very noisy, right? It's very chaotic. It's hard to understand. Sometimes overwhelming. Too many social media noise, tweets. It's very noisy. How do you, learn how to extract some kind of useful information? So therefore, we propose the system, the Huli system. Basically, the Huli system is that it takes advantage of the social media. The immediacy, the quick response. A lot of neighbors are talking about. Huli takes advantage of those, or take advantage of Twitter, and it reviews some kind of latent neighborhood information. So essentially, you can view Huli as a filter. Given input tweets volume, and basically Huli will filter out the noises and present you information about the events in my neighborhood, hot topics in my neighborhood. Who are most active neighbors, and what are the most popular places that people are talking about in my neighborhood. Probably, I can take a look next time, right? A lot of my neighbors seems like they're enjoying this bar, and I have been there, and probably I can check this time, and check out this next time. So here's the interface of Huli, and we also developed a mobile version of Huli. So basically, Huli has 4 components. The first component is the trending events. The trending events in your local neighborhood, which is driven by the DIMA, event detection algorithms directly. And it also has, it also displays the hot topics, the top topics, the most popular, topics in your neighborhood. And it also shows, the active people, your active neighbors, about in your neighborhood, and the most popular places. So these components, the popular places, basically we find this information using information extraction techniques. And for the people, we basically, run a page rank, a very similar algorithm to PageRank on a social graph. And for top topics, we just gather all the words and rank by their TIFF IDF scores. And for the the trending events, as I said, we use the DEMA algorithm directly from this event readout toolbox. Okay. So to evaluate the Huli, right? Because it's a system, we build a system, and to evaluate this, we actually need the human studies, right? And we basically invite 13 people in the certain local Seattle city into the lab, and use Huli, and you also use Twitter as the information source to do this full kind of neighborhood seeking task. Want them to say, okay, use Huli, you want to learn or give a neighborhood, say, Capio, right? What are the most events? What's the most related events? So I'll ask you to find those kind of events using Twitter and use Huli, and then so on. So the performance of Huli is very good compared to Twitter. And people basically find that using Huli, you can very easily to complete those tasks. And it's also very useful, has a better overview of the neighborhood and give you a better sense of the neighborhoods, because you can see, okay, just in one single interface, you can immediately learn, okay, what's going on in my neighborhood, or what are the people in my neighborhood, the places in my neighborhood, right? I give you a better sense of, the community feelings. And here's an interview that we did after, the task. So basically, people like Huli a lot, and they basically find, okay, Twitter is not set up for communities, and the Huli functions is amazing for this, right? So they can learn, okay, better about their neighborhood. Because a lot of people, they want to learn, but they don't know how to learn. That's the problem, and the Huli basically solves this problem, right? So, as a summary, Huli, which is the local information gathering tools, we build on top of Twitter. They take advantage of Twitter, the immediacy, the advantages of Twitter, such as immediacy, the community feeling on Twitter, but it filters out the noise of Twitter, and it has very promising feedbacks from the local residents. Okay, next I want to talk about the event enrichment task, right? And that is that how do we get the additional event information to enrich the event context? So again, this guy is here, and this event is happening here, right? And some events are happening here, and this guy is occupied, and this journalist cannot move to these events to get the information. So he has to leverage some help from the others. And one particular way to do this is using the cross-sourcing approach, right? Using a cross-sourced scheme. Basically, cross-sourcing has been a research topic in recent years, and spatial cross-sourcing since last year has also been very popular in research, And one can imagine, okay, here are some possible solutions to, gather those informations, using a crowd for this journalist, right? And a possible solution is like this. So for each event spot, the journalist can send a request to find a group of volunteers who are nearby the events, right? And they can assign them to the event enrichment task, such as take 5 photos of this event at this place at P1, right? Take another 5 photos at P2, things like that. Or take a video of P1, like that. And once the volunteers complete their task, the collected data actually are sent back to the requester. So without going to the spots in person, they can just use this kind of scheme to do the job. The journalist can use this scheme to do his job. However, there's some problems, especially in the real world scenario, right? So in the real world scenario, workers need to get rewarded. So there's no freedom, right? You have to pay them in order to ask them to get the job done. But due to the limited budget, right? I only have $100, right? So on what criteria should potential workers and spots to be selected? We cannot select random workers or assign them to a random spot. Given the limited budget, we have to assign them to the best spots. So just use this limited amount of money, we can get enough information out of it. And the next one is that, so the next kind of drawbacks or the problem of this possible solution is that the task assignment, the worker spot assignment, they always assume that they have uniform utilities. But the thing is that in the real world, right, and the same user, like user A assigned to the same spots S1 and user B assigned to the spot 1 may have different utilities. Maybe A is more experienced, maybe the spots S1 is more informative than spots 2, right? So how do we basically quantify those kind of ununiform utilities? And the last is that they assume, the very important problem here is that they always assume the volunteers will accept and complete the job all the time. But in reality, that people may drop the ball, right? They may not accept and complete the task. So there's certain uncertainty here, right? So maybe 50% of chances that they will do the job, the other 50 will not do the job. So how do we quantify such uncertainty? So we propose this CrowdX systems to handle this challenge. So essentially, the CrowdX system is our first generic spatial crowdsourcing system to date. Okay, so CrowdX system basically utilize a utility theoretic approach which consider the workers' event sports jointly and select the workers' sport assignment that simultaneously maximize the overall utility and achieve the low cost within a given budget. Right? As you can see, this is optimization problems. We want to optimize the overall utility, while we have this constraint that we have to consider, which is we have a limited number of budgets. For a journalist, they may have a limited budget to spend, right? So given $100, how do you get most of it? Then we developed 3 models to handle the challenges that I mentioned before. The first model, we basically assess non-uniform utility of each task assignment, each worker spot assignment. And we also have a model to estimate the expected cost for each worker. And we have the probabilistic model to quantify the worker's uncertainty here, and which I will describe later. And to handle these optimization problems, we basically provide a very efficient greedy algorithm, which is guaranteed to provide near optimal solutions for this very hard NPR optimization problem. So here the problem formulations for CrowdX. Essentially, as you can imagine, CrowdX is a task allocation problem, right? We need to maximize utilities and achieve low cost within the budget. So the ground set, so we first have the ground set of workers, a set of workers, right? The worker candidates. And we have a ground set of advanced sports, the sports candidates. And for workers and the sports, we have W, which is a Cartesian product of U and S. And essentially what we want to do here for CrowdX, given limited budget, is that we want to select a subset of this worker sport assignment, W prime within W, such that it will optimize or maximize the overall utility of this kind of assignment. While subject to, the certain constraint here is that the cost of hiring those people will be less than the budget, where the budget is greater than 0. And the F function is a utility function, and the C function is a cost function. So what this problem, this formula tells us is that, let's say, so here is a matrix, right? So each row represents one worker, and each column represents one spot. So essentially what we want to do here is that given the assignment, the worker spot assignment, like W1 to X1, W2 to S1 like that, we essentially want to select a certain cells here that the summation of these cells will achieve the maximum utility, while the cost here will within the budget. So how do you do this job? So first, I want to talk a little bit about the utility function. How do we define this utility? So utility function, we believe that it should have 2 properties: the representativeness of the selected spots and the quality of the selected work. Again, right? Because we have certain budget, we cannot, select all these users and assign them to all the spots, right? We cannot do that because we have limited budget. So therefore, for the selected ones, we need to consider how good the representative is, how good and how representative they are, and how high quality they are. So in addition to the representative, we further define that the representativeness should be about 2 properties, informative and diversity for each spot. So here, L function is about informativeness, and R function is about diversity for the selected worker spot assignment. So what informative diversity means here is that we basically want to select the most informative spots, right? By just dispatching the users to these spots, they can get enough information that they can cover the rest unselected spots. And for the diversity here, we mean that events already have multiple aspects, right? Different events have different aspects. So we want to basically select a certain spot that can represent all the aspects all the aspects as complete as possible. So what these two mean here is that why we have this function to combine them together and using the controlled by these different parameters here is that, let me give you an example. Here what we want to do, as I said, is that we want to maximize the overall utility for the worker spot assignment and subject to the constraints, which is that the total cost should be below the threshold. And this is actually the NPR problems that people can prove. And but luckily we have a very unique advantage of we can prove that this f function is a sub-modular function, right? By sub-modular, based on this definition, a function is sub-modular if the one element from the subset is added there and you get a better gain. So we can prove that the L function, which covers the the coverage or uniformness, and the R function, which covers the diversity, are sub-modular, and also we can prove that Q is a modular function. So based on this theorem, that this whole function is sub-modular. Given this function is sub-modular, we can derive a greedy algorithm, a very efficient greedy algorithm, to achieve to maximize, to solve this optimization problem with a fixed bond. So here is a some evaluations of quad X and compare that to the baselines. And in general, quad X is very scalable and very robust, and actually achieve much better higher utility than the other baselines. And to summarize, we developed the quad X, which is the first very general spatial cross-docking system to date. And we also developed a greedy algorithm to solve this very hard and incomplete optimization problems, and also we demonstrate quad X significantly outperformed baselines of the other competitors. So last, I want to talk about some of the insights that we learned. So far, right, we analyze events using social media data, the input social media data. But little is known about the input itself, right? We do not know, okay, why people tweet about this event? Why some people tweet more about this event than the others? So what we want to do here is that we ask some kind of interesting questions, like, that the people, post tweets about the event because they're interested and things like that. Essentially, we want to learn here is that what kind of factors affect people's engagement on events, with events on Twitter. So we consider basically 5 broad factors inspired by the work in social science, the linguistics, the computer-mediated communications, and we get these 5 different broad categories. The Twitter activities, we want to say how the people's activities in the past can affect their engagement in the current event. Like whether they will engage it, and once they engage it, how deeply, what's the degree of the engagement? Like how many tweets that they will tweet, will post it about this event. And also we want to learn whether the past topics, the topic of your past tweets, whether that has any effect, and the user types and the geolocation. For example, whether you will engage more if the event is a local event, right? And last, we want to say the effect from the social media structure. And we have 2 dependent variables in this analysis. The first one is we want to see the presence of the person's Twitter engagement, whether you will tweet about the event or not. So it will be either 1 or 0. And the degree of the engagement, which is the number of tweets that you will post. So before doing the kind of regression analysis, so here's the data set that we used for this study. Basically, we get about over 400 events from 20 million tweets from Twitter Firefox, and also we gain the events geolocations and the user geolocations, because we need to learn the effect of the geolocations on people's engagement. So here are some results, and the more results are in the meditation, but I want to highlight some kind of interesting ones here. Is that so? The question here we want to answer is how and to what extent do different topics of the event that affect the degree of the engagement. So then we find different genres or different topics of the event actually affect the degree of the engagement, different topics, right? Like the political, the entertainment, the science and technology events. Basically, when people engage in those events, their engagement largely depend on the content of their past tweets. So what this means is that if you post a lot of tweets about the gadgets, right? So if you're a very geeky person and tweet a lot of tweets about this event, then you are more likely to get engaged more, post more tweets on this current event, say Apple released a new product, so you are more likely to engage more. But this we just find evidence for this kind of three types of events. But in our study, we investigate other kind of events, but we didn't find kind of influence like this. Also, we find that engagement in sports events and the local events tend to correspond to more closely with users' geolocations. Like I'm in Tempe, in Arizona, probably I'm very interested in the Sun Devils, the sport team in Sun Devils, but less likely that I will be very interested in, say, Huskies, which is University of Washington sport team, right? Because the geolocation matters, and also my belongings matters here. And next, enabled by the event radar toolbox, the computational from the event radar toolbox, we are able to discover some kind of interesting hidden patterns of people's engagement with events on Twitter. So here is a graph that shows, so the y-axis is the number of tweets, which ordered along the timeline of the event. And the y-axis basically stands the percentage of specific, episodic tweets. So what we find here is that I separate them into three chunks: the before, during, and after the event. So what we find is that before the event, most responses are either tangential or about very high level. They're very general because they do not know anything about the event. So they tend to be very general because they don't know any context. But towards the beginning of the event, we monitored a very rapid increase. And during the event, we can see a lot of fluctuations here, right? And which sort of means that very controversial topics people are talking about. So this data is generated based on the I think Obama-Romney debate, and you can see a lot of fluctuations here. Basically, it indicates that it's people have different engagement with respect to different topics of the event. Because this as you can remember, the specific tweets we basically find specific tweets means it talks about the particular segments of the event, right? So essentially, this this fluctuation indicates that people have different engagement into different segments of the event. And as you can see here, that after the event, the engagement level suddenly drops down, right? People become less interested. So then we make this. The first insight is that the responses tend to be very general, steady, before and after the event. And while during the event, they are more specific and episodic. They are influenced by what people actually are saying here. And next is that we look at the tweeting behaviors during the engaged events. So again, the x-axis is the timeline of the event, and the y-axis actually is a segment of the event, right? So for the Obama-Romney debate, we have these 14 segments where each segment talks about a particular set of topics, and each dot here means a specific tweet that is talking about the particular topics within this segment, about this segment. So, for example, the tweets appearing here talk about the topics in segment 4, about healthcare topics, for example. So now we make a very interesting observation here is that we draw a vertical line here, and we can observe that assume at this time point Obama and Romney are debating about topics around here. So this is ordered by the timestamps of the event, right? Timestamp of tweets, which means the timeline of the event. So assume that Obama and Romney talk about the events around here. And we can say actually, because there are some dots still here about the segments that already been discussed, we can say that, people can talk about the things that have been discussed before and being discussed now. But also, what we find is that people can actually talk about things which I expect to be, like at this point, there's still many tweets here, right? Other people are talking about the kind of topic that will come later. And therefore, based on this, we make the second kind of insights or observation here is that the topical context of the tweet did not always correlate with the timeline of the event. And the event segment can be referred by a special tweet at any time, right? Regardless whether it has been already occurred, it occurred right now, it's being discussed right now, or will be discussed later or occur later. So essentially, so this observation is kind of interesting. So we did a similar studies on both domestic events and international events, and we find basically this kind of situation happens much more in domestic events than the international events. And we basically, sort of, believe that okay, because it is the massive events, and people have more context about, okay, the topic of events. Like they can sort of, learn or sort of predict what, let's say, if it's a Obama-Romney debate, right? They can sort of learn, okay, what Obama and Romney will say later on, even before the topic is coming. Like they can foreshadowing those kind of topics. Therefore, this situation happens a lot. But for the international events, like we did a similar study on the Obama's Middle East speech, and we didn't find, many tweets that talk about the future kind of topics, which because, many people, they don't know, okay, what these events are really about, right? Because the data we have mostly from US. So here is the summary of the contributions that made in my dissertation. So we have basically two set of kind of contributions. So we made the most technical contributions. We built the event radar system, right, which is a very powerful, automated toolbox to handle 3 core event analysis, tasks. Event characterizations, we developed ETLDA to learn the topics, to learn the segments, to learn the inference of the event, and sort extent, which is to learn the sentiment of the event based on the tweets. And we also developed, the CrowdX, the spatial crowdsourcing system to help a journalist to gather, event information without traveling to regions, right, in person. And also we developed DEMA, the unsupervised event detection algorithm, to recognize events, the trending event from a stream of noisy tweets. And based on DEMA, we also developed Huli, which is a web interface that facilitates information seeking for local communities. So using Huli, you can readily learn what's the trending events, what's the top topics, and what the top people and the most popular places that people checked in my neighborhoods. And last, we made some scientific contributions, and we gained insights into the factors affect people's engagement, with respect to different topics and geolocations of the event like that. And also we learned, we discovered some kind of interesting patterns of people's tweeting behaviors. So along the line, I've done other kind of works. So the most recent work is that we look at the Instagram, right? So a lot of people, use Instagram these days, and they don't know why. And we basically try to understand why people are so into Instagram. And the study we did is that, we use a lot of different computer vision algorithms to make, to classify, to do the clustering on top of Instagram photos, and we found there are 8, very distinctly full categories about like friends, about food, gadgets, selfie, like that. And based on these categories, and we sort of help organize the first ever Instagram content, so everything is still on. So the organizer basically sent us emails saying whether we can derive our rules, competitions based on your work. We said okay. And we also received some kind of coverage recently, just like 2 weeks back, from Yahoo News and ABC News. And I also did some analysis, some linguistic analysis on Twitter, which appeared, in my WSM like last year. Is that what we do here is that we want to learn, okay, game tweets are very popular. What are the kind of linguistic aspects of tweets? And how formal the Twitter language is. So we basically gather the data from blogs, from the newspapers, from the chat, like SMS, and we basically, use a set of linguistic features, a lot of measures to see, given a spectrum of different mediums, how formal, how to position on Twitter language, the tweets on this spectrum, wide spectrum of different mediums, how formal it is. And surprisingly, we find that basically the English tweets on Twitter is very formal, which is kind of contradict to common sense. Like a lot of people say, people can write very random, irregular, a lot of typos in their tweets, right? So some people even say that Twitter is ruining English. Then the fact is that given the data we have, actually find that in general, Twitter are very kind of formal. It's kind of formal language, and the formalness is very close to email. And why is that? So we do some analysis, and we believe, okay, because Twitter right now is being used as a news media. A lot of news agencies, a lot of people will spread news on Twitter. Because news in general are very formal, right? Like New York Times, they will use very formal language. So that somehow the vast news-related tweets somehow elevates the overall formalness of tweets. That's the conclusion that we have. I also did some analysis of AI planning, applying AI planning to crowdsourcing, and some database stuff over the years. And here the publications are published. and some of them are covered in different press and have some, citations, I would say, and over 100 citations within 2 years. And so before I end, I want to thank my collaborators, the past collaborators, and the current collaborators. Thank you all, and I really enjoy collaborating with you. And that's it. Thanks a lot.
Okay, so we have